two case studies. So here is benzene plus ethylene alkylation gives you ethyl benzene. Okay, ethyl benzene is polymerization of ethyl benzene gives styrene. Okay, which is a polymer. The ethyl benzene further alkylates with ethylene to give diethyl benzene C10. Okay, and what you do is C10 reacts with C6, diethyl benzene reacts with benzene to give 2 moles of ethyl benzene. So the process is as follows: you are putting in fresh benzene, you are putting in fresh ethylene. Reactors are sized to be large so that all of the ethylene gets converted in the two reactors. Okay, outlet from the reaction section is diethyl benzene, ethyl benzene, benzene, ethylene is all converted. So in the recycle column, what you do is you recycle the benzene, ethyl benzene, diethyl benzene goes down. The ethyl benzene and diethyl benzene are separated in a product column. Ethyl benzene is taken out the top, diethyl benzene goes down the bottom. This diethyl benzene is recycled to reactor 2. Now if you look at the reactions, the two reactions that are going down, the two bottom reactions, there is the diethyl benzene formation reaction and there is the diethyl benzene consumption reaction. Second reaction is diethyl benzene formation, third reaction is diethyl benzene consumption. If you allow your diethyl benzene to build in the recycle loop, in the bottom recycle loop, in this bottom loop to a sufficient extent such that its concentration goes up, then as its concentration goes up, second reaction consumption will go up, so second reaction rate will go up, and ultimately what you will have is consumption by the third reaction, the consumption by the last reaction will balance formation by the second reaction. Yes or no? And then you will have no net formation of diethyl benzene in your process. Yes or no? This is called, now you are recycling diethyl benzene to extinction. Does that make sense? So diethyl benzene is recycled to extinction. Degrees of freedom. The first reactor has got a cooling mechanism, the second reactor is adiabatic. Now tell me what's the degrees of freedom. Of course it's written there, but justify.
2 for reactor 1.
Okay. 2 for reactor 1. How many for reactor 2? Which is the level? 1 for reactor 2. 2 each for the two columns, so that's 4. 4 plus 3 is 7, and 2 for the fresh feeds, for the two fresh feeds, so that's 9. Ethylene feed and benzene feed. By the way, note that since you are recycling C6, the reactors are operating in excess C6 environment. Yes or no? Excess benzene will make sure that ethylene is the limiting reactant, that will suppress diethyl benzene formation. Yes or no? Yeah, so that makes sense. Okay, so ethylene is consumed and diethyl benzene formation is suppressed by having excess benzene. Yeah. Now we do an optimization. Of course, this is a base case that I have taken from a paper. Okay. Mode 1. Mode 1 is given throughput. Okay, so let's just take the design throughput. Design throughput is ethylene feed rate is 630.6 kilomoles an hour. So this is given to you. Then remaining 8 degrees of freedom we optimize, and the optimizer gives us what are the active constraints. So if I look at the active constraints, reactor 1 should be operated at maximum level, it should be operated at maximum temperature. Reactor 2 should be operated at maximum level. Also, the impurity in the product should be at its maximum allowable limit. What is the impurity in the product? Any C6, any benzene that leaks down here will guaranteed end up, any benzene that leaks down here will guaranteed end up here, plus whatever is the split that is being done by the second column. So it will have diethyl, so this should be C10, I am sorry. So C10 plus C6. Impurities are C6, benzene leaking down, and diethyl benzene leaking up. This should sum to 0.1%, so that your product is 99.9% ethyl benzene. Yeah? Okay. Now that we have this, how many degrees of freedom are left? How many things are specified? Feed is specified 1, 2, 3, 4. 4 plus 1, 5 things are specified. How many unconstrained degrees of freedom? 4. At the optimum, it turns out that the reflux to feed ratio for column 1 should be whatever 0.78. It also turns out that, you see, there are two impurities here. You could have maximum benzene, mostly benzene and very little diethyl benzene, or you could have mostly diethyl benzene and very little benzene. Of course, it depends on the separation, but what would you like? The question is, how do you want to do the separation? This way or that way?
So we have to see the relative volatility.
No, it's not a question of relative volatility. Yeah, it is related, but C6, you see, it turns out you want 0.1% total impurity. At optimum, what you are finding is C6 is 0.09%. So you are basically what you are saying is mostly benzene impurity in the product. Why? These things need to be thought through. Why? Why is T reactor 1 max active? The second reactor is adiabatic, so you will maximize the temperature in the second reactor, and therefore you will maximize the consumption, the transalkylation, the DEB consumption in the second reactor, and therefore DEB will not build up to that large an extent. Diethyl benzene will not build up to that large an extent. Does that make sense or no? Yeah? You see, I want the reactor temperature of reactor 1 to be max, because that gives me the highest possible temperature in reactor 2. Reactor 2 is adiabatic. Now that the temperature in reactor 2 is, what is happening in reactor 2? Reactor 2 is basically transalkylation, the last reaction. Okay. So if the last reaction is fast, what that means is I will not be having that much DEB accumulating in the recycle loop. I don't need to accumulate it to that large an extent to balance the consumption. For similar reasons, U1 and U2 max are also active. U2 max is active for the same reason. I don't want unnecessarily to recirculate too much diethyl benzene. If the reactor level is maximum, similarly U1 max is active. Okay. Why is C6 0.09% impurity? Why is the impurity in my product mostly benzene? That's the question.
So because we do not want to let out more C10, since if we let out more C10, that means there is lesser amount in recycle.
No, it's got nothing to do with recycling.
So, like if you have
C10, how is C10 made?
C10 is made from C8 and C2.
So two molecules of C2 and one molecule of benzene are there in C10. By allowing benzene to be the impurity, I am saving on 2 molecules of ethylene. Ethylene is expensive, yes or no? Of course, then you will say that why didn't you put it at 0.1? Because if you put it at 0.1, then what will happen is that the boil up in the second column, I will have very little impurity C10 in the product, and then what will happen is the boil up in the second column will blow up. Boil up and reflux in the second column will blow up, right? But if you look at it commonsensically, yeah, it's an easily separable mixture because 2 carbon numbers are different. C6, C8, C10. So separation is not that big a deal. All my profit will then come by how much raw material I am saving. So by allowing C6 to be the primary impurity, I am saving on, I am consuming less ethylene. Yeah. That gives me slightly higher profit. It's not a big deal, maybe just 0.1, 0.2% greater profit, but nevertheless that is what is the justification. Of course, if the customer says that I want 0.05% benzene and 0.05% diethyl benzene, then it's not a degree of freedom, then it is fixed, it's specified by the customer. Yeah, but if it is a degree of freedom, this is how I would run it, because the separation is relatively easy in both the columns. Yes or no? Does that make sense? Okay. And of course your excess ratio, so 2 degrees of freedom we talked about unconstrained, L1 by F1, and the impurity benzene in the product. The other 2 I have just chosen as total benzene to the reactor divided by fresh ethylene to the reactor, and that turns out to be 1.3. So there is a 30% excess of benzene going to the reactor. Yeah, here this is total benzene going to the reactor. So this is to this is 1.3 about. Similarly, it turns out that the recirculation rate of diethyl benzene is 112.2 kilomoles an hour. This is mode 1. Agreed? So this is what the optimizer gives me. How to do the optimization, I don't want to bother you with all that, but how to use the results from the optimization for control structure synthesis, that is what we are interested in. Okay. Now mode 1 is design throughput. I want to go to maximum throughput. So at maximum throughput, well, FC2 is not specified, it is whatever it is. It's a dependent variable. It's actually a design variable. Okay. The other 4 constraints are active, and what happens is these constraints become active. At maximum throughput, these constraints are active. Earlier throughput was given. Now FC2 itself is a decision variable. Earlier FC2 was fixed, the other 8 variables were optimized.
So if it's maximum, then isn't
We don't know what that maximum is. You are maximizing FC2, but FC2 itself is a degree of freedom that's used up because it's not specified. It is free to float.
dependent on other?
Yeah, so it's not dependent. It's you got 9 degrees of freedom, and you are using all 9 degrees of freedom to maximize throughput. Earlier throughput was given. You are left with 8 degrees of freedom.
Okay, right.
Yeah. Okay. So two unconstrained degrees of freedom. It turns out that now you have XC6, the impurity of benzene in the product, going down to 0.04%. Why is that? Well, that's got to do with, I don't know, it's hard to explain. But once you look at the control system, it will become clear why that happened. Okay. If I don't explain it, remind me, I'll explain it once we go through the control system. Okay. Okay, let's put it this way. See, V2 max is active. The boil up in the second column is active. So is V1 max. Yeah. If I relax on the benzene, then I can allow more C10 in the top. So earlier benzene was 0.09%. If I reduce it to 0.07%, 0.06%, I will be allowed 0.04%. So my separation in the second column will become loose. Earlier I was only allowing 0.01% diethyl benzene at the top. Now I am allowed to let 0.04% diethyl benzene up the top, not C6, C10. 0.06% C10 on up the top, right? So the separation is becoming less stringent. If the separation is becoming less stringent, I need less reflux. If I need less reflux, boil up will reduce. But if I am keeping the boil up the same, then I can suck in more feed. That gives me a rise in throughput. But then V1 max is also active. Why did the benzene impurity go down to 0.04% from 0.09%? Okay, that's what we were discussing. It turns out that V2 max is active. Because V2 max is active, if I relax on the C10 impurity there, right, then I will have to tighten C6 impurity. Okay. So if I relax on C10, that means XC10 is increasing, which means XC6 must decrease. So as I increase the XC10 in the top, reflux would decrease. If the boil up remains at V2 max, I will need to put in more feed to this column. That means my throughput goes up, right? My FC2 goes up. I want to maximize FC2. But as I am doing that, XC6 is becoming more stringent, is becoming smaller and smaller. That means I am allowing lesser and lesser amount of benzene to leak down the recycle column, the first column. So if XC6 is becoming tighter, V1 max is fixed, there will come a stage when the feed to the recycle column will have to decrease in order to not let benzene leak out. It contaminates your product, right? So between these two extremes there is an optimum. I can't have too stringent C6 and I can't have too stringent C10. somewhere in the middle, and that middle turns out to be 0.04%, something like that. I want to maximize FC2. Okay, if I want to maximize FC2, V2 max is active. If I keep XC10 really tight at 0.01%, then that will limit how much feed I can put to the second column. If I relax this to, let us say, 0.05%, then what will happen is my reflux will go down, because now I am allowing more diethyl benzene to leak up the top. Then I can suck in more feed to this column, yes or no? Okay. So by relaxing on C10, I am sucking more feed to the second column. However, I am making the separation in the recycle column tighter, because now if earlier XC6 was 0.09%, but when you made XC10 0.05%, this must also go down to 0.05%, right? Let us say I will say, okay, I will make XC10 0.01%, 0.09%, I will make it very loose, then this becomes very tight. If this becomes very tight in the first column, V1 is at max. I don't want to let any benzene leak out. That means I am the feed that I can suck in the first column will be only so much, right? So in this extreme, in the extreme where the principal impurity is benzene, the second column becomes limiting. In the extreme that the principal impurity is diethyl benzene, the first column becomes limiting. Somewhere in the middle is the optimum that gives you maximum FC2. That's your objective, right? Therefore it goes down to about 0.04%. And of course, because you are increasing throughput, your DEB recycle increases to 230 kilomoles an hour. Okay, so these are the two unconstrained degrees of freedom. Yeah. Now let us synthesize the control system. By the way, this is the variation in FC2 with product impurity and the DEB recirculation rate. You had two unconstrained degrees of freedom, right? DEB recirculation rate and whatever was the product impurity, XC6, right? So XC6 is X benzene. The line that is in solid is the optimum, 0.04% benzene. This line dash dot is 0.01%. This is 0.09%. So mostly benzene is the dotted line, dash dotted line is mostly diethyl benzene, and the black solid line is a little bit of this and a little bit of that, comparable amounts of the two impurities, right? You can see that the throughput here is about 970 kilomoles an hour. Maximum achievable throughput is 970 kilomoles an hour, and this is occurring at about 230 somewhere around 230. Yeah. If you don't play with the product impurity, the maximum achievable is, I don't know how much, this extreme or that extreme, is about 930. So you are getting 40 kilomoles extra per hour throughput, and if you say 40 is about 4% of 1000. 970 is about 1000, right? So 4% extra production just by playing with the two unconstrained degrees of freedom. 4% is a heck of a lot. 4% accumulated over years, an year of operation will turn out to be millions of dollars or crores of rupees in extra revenue. Yes or no? Yeah. So even though it appears 0.09%, 0.01%, blah 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 blah, but it makes a difference. Of course, if the operator or if the customer is saying no, you have to have so much impurity this and so much impurity that, then it's not a degree of freedom, it's fixed, and then maximum throughput is whatever the hell it is. Now let us synthesize mode 2, max throughput. What are my active input constraints? These are active, so I keep them at max. Yeah, all right. I need to control my product impurity, right? So I do that. So what am I doing? I am controlling a tray temperature in the recycle column here. Yeah, this tray temperature is controlled by adjusting the feed to the column. Okay. Why am I using the feed? Because boil up is already max, I am not allowed to change it. reflux is also max, I am not allowed to change it. So this is what I am doing. And then this temperature set point is adjusted to maintain the benzene impurity in the product at 0.04%, which my optimizer gave me. Yeah.
So why is it linked to reflux?
Who is linking to reflux? The reflux is the product. Yeah, distillate and reflux is the same, right?
Okay. Yeah.
I mean,
Yeah.
it's just ease of drawing. That's all. Okay. So the product composition, the product benzene impurity is setting the temperature set point. Yeah. So that takes care of benzene impurity. Then I set the diethyl benzene impurity in the product as 0.1% minus whatever was the set point here. That gives me how much diethyl benzene I am allowed to leak out. So independent is benzene, dependent is diethyl benzene. Okay, the way I have drawn it. Okay. So well, that's this. And what I am doing is, I have shown that I am adjusting the reflux, but usually what you will have is a temperature controller that adjusts the reflux, and that temperature set point is being adjusted by the composition controller. But for ease of drawing, I have just drawn it like this. What you would have is a temperature controller that does this, and this set point would come from the composition controller, right? But then it becomes quite messy. I just for the heck of showing it, I just showed it like this. Yeah, okay. Okay, then you see, I am limited in my capacity to boil off. V2 max is max. I cannot boil off ethyl benzene. So if I am getting more ethyl benzene, then I can boil off to the column. Where will that ethyl benzene go? It will drop down and build up in the DEB recycle loop. Yes or no? I don't want to do that. So what do? I control a stripping tray temperature by adjusting the feed. That will ensure the feed is only so much, no ethyl benzene drops down. Yes or no? That makes sense? Okay, so that's what this temperature. Now I have done this. That is a stabilization issue. It's a stabilization issue. What do I mean by stabilization issue? If I don't control this temperature, I can have a situation where things will drop down and accumulate they'll just keep dropping down. If I am making more ethyl benzene in the reactors, then I can boil off in the second column. Where will that ethyl benzene go? It will bloody drop down and keep circulating around in that loop. Yes or no? I don't want that. That's a stabilization issue. That's like a level is building up and up and up. It's not a level, but so I put a temperature controller there. That's a stabilization loop. Okay. Now that I have done this, I put in level controllers. Note that reactor 2 outlet valve is taken. I have to control level of recycle column bottom. The only valve available is here. So what I do is this, because this valve will get used to control level of this guy, right? So the only way to control level here is this way. The only way to control level in the first reactor is this way. Only way to control temperature of the first reactor is this way. And of course these set points must be max allowed. That's because my optimizer said so, and it makes physical sense actually. Yes or no? Okay, fair deal. Then I put level controllers on the column, pressure controllers on the column. Okay, so this level controller works this way, this level controller works this way, this level controller works this way. Pressure controllers are standard using condenser duty on both the columns. What about this level? There are no valves to control this level. The only valve that's available is this guy. You see what I am saying? Because I have two constraints active on the column, and I am also wanting to control the benzene impurity. One of the levels I don't know how to, I don't have a local valve to control one of the levels. This is what is only left. This is what is left. So I put in this level controller. Okay. Dal diya. It sounds very odd, but if you think about it, it actually makes sense. Where is the ethyl benzene and the diethyl benzene accumulating inside the plant? It's accumulating here. Benzene is removed. Ethyl benzene and diethyl benzene drop and build here. So if this level is dropping, what does that mean? That means I am making too little product in the reactors. If this level is dropping, that means I am making too little product in the reactors. Increase the ethylene. If this level is increasing, I am making too much product. Reduce the ethylene. That's what this level controller is doing. it makes sense. Only problem is, if I make a change in the ethylene valve, in the ethylene flow, how long does it take for that effect to show up in the level? It turns out that because these two reactors are CSTRs and they have been designed for complete conversion of ethylene, residence times are very large, 1 hour in reactor 1, 1 hour in reactor 2 at the design condition. So, if I do something here, by the time it has an effect on the level, the tank may
changing the ethylene input stream, then we should change the benzene input stream also.
The level controller will take care of that. We have, that's what I am trying to show. If I do it this way, this is the control structure that comes. But for the residence time problem, if I had a plug flow reactor, in fact we have done simulations and shown that if you have a plug flow reactor, their residence time is not an issue. You make a change here, right, because the flow is compressible flow essentially. Yeah. So, but for the large residence time in the reactors, this scheme would have worked. It turns out that for this process, it won't work because the reactor residence time, total reactor residence time is of the order of 2 hours. Had it been of the order of 5, 10, 15 minutes, it would have worked. Okay. Alright.
So, we don't need a very tight control.
No, it's not a question of very tight control. You see, what happens is if even for 1% change, even for a 1% change in what is the throughput, there is no throughput manipulator here. So, even for a very small disturbance, let us say a 1% change in throughput, okay, or 1% change in one of the set points, either temperature or pressure or composition or whatever, even for a very small change in a set point, what happens is this bottom level in the recycle column either overflows or runs dry. That means the level control is fragile. ये बात हजम हुई? It's very fragile. It's very fragile because I make a change in ethylene. By the time the effect comes to the bottom level, it may have run dry or it may have overflown, and that is what actually happens. Okay, so it is fragile, and it's fragile because of the large residence time in the reactors. But in terms of an attempt, everything is tightly controlled. All the effect is being taken in the 2 levels, 4 levels, 1, 2, 3, 4 in the columns. Reflux, everything is tightly controlled, and all the variability is being taken in the levels and the utilities, steam and cooling water and this and that. Do you see what I am saying? However, it turns out that it cannot work because of this. Yeah. So now I need to do something. What do I do? I say, well, this level is fragile, I need to make it more robust. So what do? I say, well, take that temperature controller off. Okay. Now I have a problem. What is the problem? And then I say, okay, I will maintain the ethylene in ratio with the total benzene. Okay. See, what did I do? This was problematic. So I took this temperature controller out and put a level controller instead. Now this valve is free. How do I manage it? I will say I will keep the ethylene in ratio with the total benzene. Okay. So now these are my 2 unconstrained degrees of freedom. 1, 2. Yes or no? Okay. Now problem remains here in the sense that I am setting the ethylene independent of, there is a problem in this control structure. What is the problem? And I have already described that problem. What did I take out? I took out the temperature controller. What was the temperature controller supposed to do? Ensure that ethyl benzene does, if you are producing more ethyl benzene in the reactor and you are limited by V2 max, you cannot boil it off, it will accumulate in the DEB recycle loop. To prevent that, I had put that temperature controller. Now I have taken that temperature controller out. Now this problem exists. So what will we do? We do this. This, or you can even control a temperature. If ethyl benzene drops down, this flow will increase. The bottom flow, this flow will increase. If ethyl benzene is dropping down, composition, I don't want to measure compositions. because composition is the only product purity you will get, nothing else you will get. You are still supposed to operate it without any composition. Temperature, pressures, flows, that's all that's available. Composition very rarely. Only place where people are willing to measure compositions are product, because that's what they are supposed to sell. They have to guarantee to the customer, so okay, wahan pe they'll make some measurements, but the rest is not available. Okay, so what I do is this. Now does this make sense? Does this make sense or no? Yeah. So now these are my two unconstrained degrees of freedom. This and this. These two set points the operator can play with. These are the same as I had told you earlier. Product impurity, product benzene impurity, and DEB recirculation rate. Okay. Alright, so I have synthesized the control structure. Now I want to reduce throughput. What will I do? So I have got my two unconstrained degrees of freedom. I want to reduce throughput. What will I do? The first thing I will do is take it to 0.09%. Throughput will reduce from 970 to about 940, something like that. Once I have done that, what I will do is I will take this from 230 to whatever it was, 112, right? So let's get back. So originally this is my throughput manipulator. I want to reduce throughput. I'll change the product impurity mix from about the same impurities to mostly benzene. That's what I do. Once that is done, I move the throughput manipulator here, go from 230 to 112. When I do that, my production will decrease further by about 4 or 5%. Okay. Then if I want to reduce production, it turns out that V1 max is the last constraint to have become active. For this process, it turns out that V1 max is the last input constraint to become active. So I use that as the throughput manipulator. Now as I am reducing the throughput, if I keep V2 max at V2 max and L1 max and L1 max, what's the problem? If V2 max is kept at V2 max, what that means is boil up is large, therefore I am boiling it up. To not allow the diethyl benzene to leak up the top, I will have to reflux more. Yes or no? So I am unnecessarily recirculating things here in this way, and I am wasting steam. Yes or no? Okay, so once the throughput has been reduced sufficiently, I will take up temperature control whenever I can of the stripping tray. Okay. Same thing here for L1 max. As I am reducing the throughput, I will not, again, if L1 is kept unnecessarily at max, I will get extra recirculation. Yes or no? Yes or no? To prevent that, what I am saying, whenever reflux can be maintained in ratio with the feed, I will take up ratio control. Now let us go in reverse. I am at low throughputs, I am increasing the steam here. As I am increasing the steam, all flows are increasing. Flow to this column is also increasing, in ratio reflux is increasing, but then when reflux becomes max, I cannot maintain it in ratio anymore. If I cannot maintain it in ratio anymore, well, that's it, then L1 is at L1 max. I am increasing throughput, I am increasing the steam to the recycle column further, throughput is increasing. Then what happens is the boil up in the second column reaches max. Well, if that reaches max, I cannot control the temperature anymore. If I can't control the temperature, well, that's what is given up. Yeah. Then I am increasing throughput further, and then what happens is this becomes max. Then what I do is I change the DEB recycle rate from 112 to 100 or 230. I keep increasing it. Okay, throughput increases. Then what do? I change this from 0.09% to 0.04%, right? So this is what will take me from low throughputs to high throughputs. As I am going the other direction, you see, so as I am increasing throughput, I give up control of things that I was controlling as constraints become active. As I am decreasing throughput, I take up control of things that make economic sense. It does not make economic sense to unnecessarily recirculate too much in any of the columns. Yes or no? In fact, instead of doing the ratio, I could have also, instead of So when this, whenever I'll take up temperature control whenever I can, and I'll take up ratio control whenever I can. I could have also controlled the Tate temperature by adjusting the reflux in the rectifying section. I could have done that too. It's just that this is simpler. Yeah, this is much simpler. Okay. Note, this is something that I want you to notice, that everything that you are doing here comes from the constraints, from the set of active constraints. What should be my throughput manipulator? Should I use boil up to control temperature? Well, if it's active, no. Is it critical to control the benzene leaking down the first column? Yes, because otherwise it will contaminate my product. So even though V1 is active, V1 max is active, I still need to control it. Therefore, this loop has to be there, right? It is all coming from what are my constraints that are active. The structure is following from. Now in this case, what we have done is, we have gotten robust control of the level in the first column, which was not being controlled properly because there was a very unconventional loop there. What are we losing? What is it at the expense of? It is at the expense of large swings here in this loop, because now the control of this guy is being done by ethylene. When I maintain this flow by changing ethylene, it takes a long time for its effect to come in the DEB. When I change ethylene, its effect on the will be after a long time, right? When I was doing this, its effect was immediate, right? So I have made a compromise. The compromise is, what is the compromise?
Sir, how exactly we decide which are the active constraints?
Optimizer. This is, see, I told you this and that are the active constraints, right? It came from the optimizer.
Which one will active first?
That comes from the optimizer. So you do your optimization for various throughputs. At this throughput, no constraints are active. Then as I increased my throughput, this constraint became active. Then as I increased my throughput further, that constraint became active. Then as I went to my maximum throughput, this was the final constraint to become active. Right? So you will have to do bunch of optimizations. I didn't show you any of that. I just gave you the result of the optimizer that was relevant to synthesizing the control system.
So we can't do it manually.
You will have to apply a lot of common sense to do it manually. You can talk to operators, then they will tell you, okay, when I try to jack up throughput, this becomes active, and then that becomes active, and then that. Operators can also tell you that. So either from a model of the process which you optimize using an optimizer by playing with the degrees of freedom that are there with you, or by using some engineering common sense, which is actually quite rare. Now conventionally what you would do is you would flow control the limiting reactant, which is ethylene, to the reactor. You will keep total benzene going in constant to prevent snowballing and feed benzene as a makeup stream. Yeah, all right. Then the rest is level control, temperature control. These are the level controllers on the column as well as on the reactor, pressure controllers on the column. Yeah, and then you are maintaining reflux to feed ratio in column 1. You are maintaining temperature of the stripping section by adjusting boil up in column 2. Okay, and then you are maintaining the product purities in this way. Does this make sense? This is a conventional control system. Yeah, obviously you'd like to keep these at max because that's optimum. Yes or no? What are your 4 unconstrained degrees of freedom? Those are shown, I think, in green. Let's see. You maintain total benzene in ratio with the ethylene, and because you can get snowballing in the DEB recycle loop, what Lieben has suggested is that you maintain the flow of the DEB recycle by adjusting the ratio set point. Okay, this is what has been suggested in that paper by him. So I just took that structure. Okay, now throughput manipulator is the fresh ethylene. You jack the throughput up. Okay, these are your the green arrows are your unconstrained degrees of freedom. 4 unconstrained degrees of freedom, 4 green arrows. Total the DEB recycle rate 1, the reflux to feed ratio in column 1 2, the benzene impurity 3, and the temperature set point on the second column 4 degrees of freedom. Yes or no? Mode 1 we had 4 unconstrained degrees. These are the 4 unconstrained degrees of freedom. Okay. Now these are, well, what the hell am I doing? Okay, now I am going to increase the throughput and go to mode 2. Okay, go to maximum throughput. So I start jacking up the ethylene. This becomes maximum. So I can't maintain ratio, that's fine. I jack up the throughput further. This becomes maximum, I can't maintain the temperature. Same problem now occurs. I can be putting more ethylene than I can boil off. I am putting more ethylene, so more ethyl benzene is getting formed, but I am limited in my capacity to boil it off. Where will that ethyl benzene go? That ethyl benzene will build in the DEB recycle loop. So if DEB builds up here, if ethyl benzene drops in the DEB recycle loop, okay, the flow rate of the DEB recycle will go up. If that flow rate goes up, what the hell? Yeah, if that flow rate goes up, I will adjust the ratio and increase the total benzene. If I am increasing the total benzene, then the boil up in the first column will increase. And I have to send more stuff up now, so the boil up will have to increase. So what will happen is, to maintain this flow rate constant, I will start getting snowballing in. My boil up will start to increase in the first column. Yes or no? Okay. So that increase in boil up is telling me what? That I am producing more ethyl benzene than I can boil off in the product column, and it is essentially building up in the 2 recycle loops. Alright. So how do I prevent that? Well, I use a boil up controller that does this. Does that make sense or no? I use a boil up controller that does this. Okay. It appears that this is fine, because I am well, let's see if I can, pointer options, pen. I am preventing snowballing here by adjusting the ratio, and I am keeping the total benzene constant, right? So there is an impression that gets created that okay, there will be no, there will be no build up in both the recycle loops. But please note, when you think about it, what is actually happening is, I am just transforming what is happening here to here. You see, this loop is transforming here to here. Total benzene is increasing. To increase total benzene, you will actually get this to increase, the boil up to increase. Yes or no? So the problem remains. I get the impression I have maintained this also and I have maintained that also, but the moment V2 max goes active, that problem is there, and I am just transferring it from here to there. Boil up will keep increasing in order to do that. Yes or no? So therefore, to prevent that, what we are doing is, we will do this. So if this boil up is going up, that means you are producing too much ethylene, you are producing too much ethyl benzene, you can't boil it off, and it is building up in the 2 recycle loops. Therefore, reduce the amount of ethylene that you are putting in. So this loop comes in. Okay, this is conventional. But please note, I need to configure this loop once V2 max goes active. In the previous control structure, I didn't configure anything. Things are taking control up or giving control up. There is no reconfiguration of loops. Here I need to put in this magenta loop once V2 max goes active. That is an additional complexity here. Okay. So we have looked at 2 control structures. Now let us just compare their performance. Mode 1, no constraints are active, no input constraints are active, and therefore whether I am using the conventional control structure or the control structure that we have proposed, if you do a throughput change, plus minus 10% throughput change, everything is smooth. CS1 or CS2, it does not really matter. Okay, about 20 hours your response is complete. Product purity is tightly controlled, smooth response. Okay. Now if you go to max without VPC is, you know, if I don't put that loop that adjusts the ethylene in this structure and that structure, what happens in CS1, the structure that we synthesized, what I am taking as the disturbance is a 5% noise, a 5% bias in the fresh ethylene flow sensor. So the flow sensor is saying flow is X, suddenly the flow goes from X to X plus delta X when the actual flow remains X. Sensor has got a 5% bias. Okay. So when that happens, you know, what this response is essentially showing is even if you get a 5% step bias, you get a decent response, throughput goes down a little bit, but that's okay. Okay. In CS2, without that ethylene loop, without that magenta loop, okay, if you put in the VPC in CS1, what you find is, well, the throughput comes back to wherever it was. What is interesting is CS2, the conventional control structure. If you don't put in that VPC, I am at 840 kilomoles an hour of ethylene FC2. Okay. When that 5% bias in the ethylene flow sensor comes, you find that V1 keeps going and it hits its maximum limit. Okay. If I am at 850 kilomoles an hour, what I find is that when that disturbance comes, it hits its maximum limit. V1 hits its maximum limit. Once V1 hits its maximum limit, I lose control of the product purity, because now benzene starts dropping down, and you see here my product purity has gone down. I wanted it here, it's not under control, it has gone down. It may have gone down by a very small amount, but it has gone down and gone down for good. I cannot back it up, right? So what would an operator do? He will say, well, I am producing junky product. He will never exceed 840 kilomoles an hour. He knows, because the moment I go to 850, sensor mein gadbad hoti rehti hai, the sensor keeps going here and there. If it goes there and I am having a cup of tea, I will be producing junk. Or I am not attentive enough, 15 hours later I will be producing junk. And then the next operator wouldn't know why that is happening, because the shift has changed. Okay, so what he will do is, let's forget about 970 kilomoles an hour, we will just operate at 800, 820, 830, but never exceed 840. So without that VPC, you are stuck at 840. What was the maximum capacity of this plant? 970. How much? 13%. That's a big amount of difference. Okay, and it's all got to do with the control system that you've implemented. Yeah, same process, same everything. This control system that accounts for what constraints are going to become active, right? That is able to get you to whatever was the maximum achievable. This control system will fail. Then when you put in the VPC, sure, maximum achievable is 970, I believe. Okay, this is the maximum achievable. You are actually slightly below. Why are you slightly below? Because there is a transient in the boil up in column 1. That transient can never exceed 977 or whatever is the limit on that, whatever is the red limit. So I am operating at about 20-25 kilomoles lower boil up in the first column. That corresponds to a 5 kilomole per hour loss in throughput. So now the process is stable, but instead of getting 970, I get 965. This is only for one disturbance in the flow sensor ethylene. There are n number of disturbances operating at any given point in time. Not only the flow sensor, here the DEB recycle flow sensor, the total benzene flow sensor, the temperature sensor on the column, the heat loss in the column, day, night, etc., etc. All these things are operating at the same time. Okay, so each one of these disturbances will add an extra back off. So what seems like okay only 0.5% loss may actually turn out to be 1 or 2% when you take the effect of everything together. 1 or 2% throughput loss because of back off in the boil up, integrated over an year of production, will translate to millions of dollars, right? So here is the comparison. Basically what I wanted to draw your attention to was this versus this, right? That's a heck of a lot of difference. 12%, 14%, I don't know how much more, greater than 10%. Okay. Okay. It's a big difference in throughput. Okay. So, well, that's the point. Then I think last but not least, you keep changing the set point. You want to increase the throughput, so what we are doing is we are increasing the V1 set point by 10%, okay, and taking it to max. And what you find is that the FC2 keeps increasing. The rate of increase changes because constraints are becoming active. So L1 becomes active here, so somewhere here L1 becomes active, somewhere here L2 becomes V2 becomes active, and finally V1 becomes active someplace here. In spite of that, I am still able to jack up the throughput by playing with those two unconstrained degrees of freedom, 112 kilomoles an hour to 230 kilomoles an hour, and benzene in impurity from 0.04% to 0.09% or 0.09% to 0.04%. Does that make sense? So I am getting an increase in throughput, and I am able to get to whatever was my maximum capacity, 970 kilomoles an hour. Okay. What happens in mode 1 to mode 2 transition without the VPC? If I don't put the VPC in CS2, this is CS2, the conventional control system. I am jacking up the fresh ethylene feed rate by 10% every 15 hours or 20 hours, I don't know how much. Okay, and then what happens is V1 hits max and I lose product purity control. So an operator would say, don't go beyond this, इससे ज़्यादा ऊपर जाओ ही मत, right? And you are losing this much throughput. Even though the plant is capable, your control system is basically screwed up. It's screwed up because you didn't take into consideration what constraints are going to become active and what am I going to lose because of that. It turns out here what I am losing is product purity control. Too much benzene contaminates my product. That's because V1 max becomes an active constraint. That's the problem. Yes or no? I think that's that. We'll finish it here. There's another case study. Well, so summary, more than 10% control structure dependent throughput loss. Okay. Near optimal operation across entire throughput range is possible using a very simple control system. And that simple control system does not require to configure additional loops when a constraint becomes active. You see, that's very important. And conventional throughput manipulator location at the process feed is not recommended. The throughput manipulator should be at the boil up, which is the last constraint to become active. Yeah. In this case study, actually, if there are 7 or 8 degrees of freedom, all degrees of freedom are lost. At maximum throughput, 8 active constraints.